Put on your sweatbands, folks. It is officially leg day for your brain. Welcome to the Ultimate Pharmacy Math Marathon. We are crushing 50 realistic, high-difficulty questions back to back. We aren't just doing the easy reps. We are heavy lifting the exam-style monsters, layered scenarios, complex dilutions, IV flow rates, and more. I'm walking you through every step, line by line, so you don't just get the answer, you learn the method. Grab your calculator and a notepad. Let's get certified. This is PTCB Prep Guide. Let's kick things off with a standard dosage calculation. Question 1. A patient weighing 198 pounds is prescribed a medication dosed at 15 milligrams per kilogram per day to be divided into 3 equal doses. How many milligrams will the patient receive per dose? Is it A, 900 milligrams, B, 1350 milligrams, C, 450 milligrams, or D, 45 milligrams? Go ahead and pause the video here. Read the question on the screen, get your calculations done, and when you are ready, unpause, and I will walk you through the actual steps to solve this. All right, let's break down the calculation. The first step we need to do is conversion. We take 198 pounds and divide by 2.2 to get 90 kilograms. Then, to calculate the total daily dose, we take 90 kilograms and multiply it by 15 milligrams per kilogram, which equals 1350 milligrams per day. Finally, we divide that total daily dose of 1350 milligrams by 3 doses to find the amount per dose, which is 450 milligrams. So our calculated answer is 450 milligrams. Let's lock that in and check if we did it the right way. Yes, we got it right. Option C, 450 milligrams is the correct answer. The key is to notice the divided into 3 equal doses instruction. A common error is stopping at the total daily dose of 1350 milligrams. Moving on to some business math. Here is an inventory pricing scenario. Question 2. A pharmacy purchases a bottle of 100 tablets for $85. The pharmacy wants to achieve a 25% markup on the cost. What should be the selling price for the entire bottle? Your choices are A, $106.25, B, $113.33, C, $63.75, and D, $21.25. Take a moment to pause right now. Crunch the numbers yourself, and once you have an answer, hit play and we will review the solution together. Here are the steps. First, we calculate the markup amount by taking 85 multiplied by 0.25, which gives us 21.25. Then, we add that markup to the cost to find the selling price. So, 85 plus 21.25 equals 106.25. We landed on $106.25. Let's see if that matches our options. Correct. Option A, $106.25 is the right answer. Markup is calculated based on the cost price. The trap is confusing margin with markup or subtracting the percentage instead of adding it. Now, let's look at an IV infusion rate problem involving drop factors. Question 3. An IV infusion of 1,000 milliliters normal saline is to be administered over 8 hours. The drop factor of the tubing is 15 drops per milliliter. What is the flow rate in drops per minute? Could it be A, 21 drops per minute, B, 63 drops per minute, C, 125 drops per minute, or is it D, 31 drops per minute? I encourage you to pause here. Read the details carefully, solve for the flow rate, and then I'll jump back in to show you the method. Let's work through this. Step 1 is to calculate the flow rate in milliliters per hour. So 1,000 milliliters divided by 8 hours equals 125 milliliters per hour. Step 2 is to convert the total time to minutes. So 8 hours times 60 minutes per hour equals 480 minutes. Step 3 is applying the flow rate formula. We take 1,000 milliliters times 15 drops per milliliter and divide that by 480 minutes, which equals 31.25 drops per minute. Finally, in step 4, we round to the nearest whole number to get 31 drops per minute. Our result is 31 drops per minute. Let's lock it and reveal the correct choice. Spot on. Option D, 31 drops per minute, is the correct answer. Always round drop rates to the nearest whole number, since you cannot set a partial drop. 125 is the milliliters per hour rate, which is a common distractor. Next up, we need to interpret a SIG code to find the total volume required. Question 4. A prescription is written for amoxicillin 250 milligrams per 5 milliliters. The SIG reads 1 teaspoon PO, TID, times 10 days. What is the total volume required to fill this prescription? Option A is 100 milliliters. Option B is 150 milliliters. Option C is 300 milliliters, and option D is 50 milliliters. Hit pause and try to work this out on your own first. When you're done, I'll guide you through the conversion and calculation. Here is the calculation. First, convert the household unit to metric volume, knowing that 1 teaspoon equals 5 milliliters. Next, calculate the daily volume by taking 5 milliliters multiplied by 3 times per day, which is 15 milliliters per day. Finally, calculate the total volume for the duration by taking 15 milliliters per day times 10 days, which equals 150 milliliters. That gives us a total of 150 milliliters. Let's verify if we got it right. And the answer is option B, 150 milliliters. TID means 3 times a day. Ensure you convert teaspoons to milliliters accurately, remembering 1 teaspoon equals 5 milliliters before multiplying by frequency and days. Let's tackle a stock solution dilution problem for question number 5. Question 5. You have a stock solution of 50% dextrose. A physician orders 500 milliliters of 10% dextrose. How many milliliters of the 50% stock solution and how many milliliters of sterile water, which is 0% dextrose, are needed? Do we need A, 400 milliliters stock and 100 milliliters water? B, 50 milliliters stock and 450 milliliters water? C, 250 milliliters stock and 250 milliliters water? Or D, 100 milliliters stock and 400 milliliters water? This one can be tricky, so pause the video now. Do your math, and when you resume, we'll verify the mixture together. Let's solve this. Step 1 is to calculate the grams of dextrose needed in the final solution. 500 milliliters times 0.10 equals 50 grams. Step 2 is calculating the volume of 50% stock needed to get those 50 grams. So 50 grams divided by 0.50 equals 100 milliliters. Step 3 is calculating the volume of diluent or water needed. Take the 500 milliliters total minus the 100 milliliter stock, which equals 400 milliliters. So we have 100 stock and 400 water. Let's lock that answer in and check the board. Great work. Option D, 100 milliliters stock and 400 milliliters water is the correct answer. This is a dilution problem. Always check that the two volumes add up to the total volume ordered. So 100 plus 400 equals 500. Coming up next is a pediatric calculation involving a suspension. Question 6. A child is prescribed azithromycin 200 milligrams per 5 milliliters suspension. The SIG is 10 milligrams per kilogram on day 1, then 5 milligrams per kilogram daily for days 2 through 5. The child weighs 44 pounds. What volume is taken on day 1? Is the answer A, 10 milliliters, B, 2.5 milliliters, C, 5 milliliters, or D, 7.5 milliliters? Go ahead and pause here. Pay attention to the specific dose requested, calculate it, and then we will go through the steps. Here are the steps. First, convert the weight to kilograms by dividing 44 pounds by 2.2, which gives us 20 kilograms. Second, calculate the dose required for day 1. 20 kilograms times 10 milligrams per kilogram equals 200 milligrams. Third, set up the proportion where 200 milligrams over X milliliters equals 200 milligrams over 5 milliliters. Solving for volume, X equals 5 milliliters. The math points to 5 milliliters. Let's lock it and confirm. Exactly. Option C, 5 milliliters, is the right answer. Pay attention to the specific request for day 1 volume only. The maintenance dose for days 2 through 5 is irrelevant to the question asked. Whoa, pause for a second. You're still here? Okay, you are officially in the top 1% of students. That level of focus is exactly why you're going to pass. Since we're on a roll, let's make a deal. I spent about 3 sleepless nights hunting down these questions, recording, and editing these slides so they look pretty for you. In exchange, you hit that subscribe button. It's free, it makes the YouTube algorithm gods happy, and it gives me the dopamine hit I need to keep making these. Plus, if you hit the bell, you won't miss the next cram session. Deal? Okay, back to the math. Let's switch gears to percentage strengths involving normal saline. Question 7. How many grams of sodium chloride are in 1 liter of 0.9% normal saline? Check these out. A, 9 grams. B, 0.9 grams. C, 90 grams. Or D, 900 grams. Take a second to pause. Check your decimals, find the answer, and then I'll show you the breakdown. Let's break it down. Step 1 is defining percentage strength. 0.9% equals 0.9 grams per 100 milliliters. Step 2 is converting volume to milliliters, so 1 liter equals 1,000 milliliters. Step 3 is setting up the proportion. 0.9 grams over 100 milliliters equals x grams over 1,000 milliliters. Step 4 is solving for x. 0.9 times 1,000 divided by 100 equals 9 grams. We calculated 9 grams. Let's see if that is the winning option. You got it. Option A, 9 grams is the correct answer. Percent strength weight over volume is always grams per 100 milliliters. A common mistake is assuming it is per liter directly, which would be 0.9 grams, or misplacing the decimal to get 90 grams. Question number 8 asks about days supply for an inhaler. Question 8. A prescription reads, albuterol HFA 90 micrograms per actuation, SIG, 2 puffs QID, PRN. The inhaler contains 200-metered doses. If the patient uses the maximum daily dose, how many days will the inhaler last? Is it A, 30 days, B, 20 days, C, 50 days, or D, 25 days? Pause the video right now. Calculate the days supply based on the usage, and then we will review the solution. Here is the calculation. First, calculate the maximum daily usage. 2 puffs multiplied by 4 times per day equals 8 puffs per day. Next, divide the total doses by the daily usage. 200 doses divided by 8 puffs per day equals 25 days. That gives us 25 days. Let's lock that answer in. Correct. Option D, 25 days is the right answer. QID is 4 times daily. Even though it says PRN, meaning as needed, the question asks for the day's supply based on the maximum daily dose. Here is a question about setting an IV pump rate. Question 9. A patient needs to receive 1 gram of vancomycin in 250 milliliters D5W over 90 minutes. What is the infusion rate in milliliters per hour? Our options are A, 125 milliliters per hour, B, 167 milliliters per hour, C, 250 milliliters per hour, and D, 333 milliliters per hour. Feel free to pause. Figure out the hourly rate, and when you are ready, I'll walk you through the math. Let's work through this. Step 1 is to convert minutes to hours. 90 minutes divided by 60 minutes per hour equals 1.5 hours. Step 2 is to calculate the flow rate volume over time. 250 milliliters divided by 1.5 hours equals 166.66 repeating milliliters per hour. Step 3 is to round to the nearest whole number, which gives us 167 milliliters per hour. We are looking at 167 milliliters per hour. Let's verify that against the choices. That's right. Option B, 167 milliliters per hour is the correct answer. Flow rates for pumps are usually set in milliliters per hour. The gram weight of the drug is extra information not needed to find the fluid rate. A quick temperature conversion to wrap things up. Question 10. Convert negative 40 degrees Fahrenheit to Celsius. Final choices. A, negative 20 Celsius. B, negative 12 Celsius. C, negative 40 Celsius. Or D, 0 Celsius. Run the conversion formula, and then let's finish strong with the solution. Here are the steps. First, recall the conversion formula, where C equals F minus 32 divided by 1.8. Second, subtract 32 from the temperature. Negative 40 minus 32 equals negative 72. Third, divide by 1.8. Negative 72 divided by 1.8 equals negative 40. The result is negative 40. Let's lock it in and reveal the answer. Yes, correct. Option C, negative 40 Celsius is the right answer. Negative 40 degrees is the unique point where the Fahrenheit and Celsius scales intersect. Knowing this trivia can save calculation time, but the formula confirms it. Let's look at an insulin days supply problem. A patient is prescribed Lantus insulin 100 units per milliliter. The SIG reads, inject 30 units subcutaneously every bedtime. The pharmacy dispenses one 10 milliliter vial. The manufacturer states the vial must be discarded 28 days after opening. How many days will this specific vial last the patient effectively? Options are A, 28 days, B, 33 days, C, 30 days, or D, 10 days. Go ahead and hit pause to work this one out. Step 1 is to find the total units in the vial. We take 10 milliliters times 100 units per milliliter, giving us 1,000 units total. Next, we divide that by the daily dose. 1,000 units divided by 30 units per day equals 33.3 days mathematically. Finally, we look at the expiration. The manufacturer says it expires in 28 days. So we have enough liquid for 33 days, but it goes bad in 28. Lock in your final choice. Spot on. Option A is correct. This is a logic trap. Even though the volume lasts longer, the medication stability ends at 28 days, so that is your limiting factor. Let's tackle a conversion problem involving grains. You receive a prescription for phenobarbital 1/2 grain tablets. The patient needs to take 60 milligrams daily. How many tablets should the patient take per dose? Assume 1 grain equals 60 milligrams for this problem. Options: A, 1 tablet, B, 0.5 tablet, C, 2 tablets, or D, 4 tablets. Take a moment to crunch the numbers. Step 1 is the standard conversion. We know 1 grain is roughly 60 milligrams. Therefore, step 2 is determining the strength of the tablet. 1/2 grain equals 30 milligrams. Next, we look at the target dose, which is 60 milligrams. Finally, we divide 60 milligrams by the 30 milligrams in each tablet. That gives us our tablet count. Ready to check our work? You got it. Option C is correct. 2 tablets provide the 60 milligram dose. Remembering that 1 grain is approximately 60 to 65 milligrams is essential for these older measurements. Moving on to an infusion rate calculation. A physician orders 2 liters of D5W to be infused over 24 hours. What is the infusion rate in milliliters per hour? Options are A, 125, B, 83, C, 42, or D, 100. Hit pause and set up your division. First, we need to match our units. The question asks for milliliters, but gives us liters. So step 1 is converting 2 liters into 2,000 milliliters. Step 2 is simply dividing volume by time. We take 2,000 milliliters divided by 24 hours. This gives us 83.33 repeating. We round that to the nearest whole number. Lock in your answer. Spot on. Option B is correct, 83 milliliters per hour. The key here is always double-checking if the volume is provided in liters or milliliters before you divide. Here is a day's supply question for eye drops. Calculate the day's supply for prednisolone 1% ophthalmic solution. The SIG is 2 drops OUQID times 7 days. You dispense a 10 milliliter bottle. Assume 20 drops per milliliter. Options: A, 12 days, B, 6 days, C, 15 days, or D, 20 days. Press pause and watch out for the abbreviations. Step 1 is decoding OU. That means both eyes. So 2 drops times 2 eyes equals 4 drops per dose. Step 2 is decoding QID, or 4 times a day. 4 drops per dose times 4 times a day equals 16 drops per day. Step 3 is finding the total drops in the bottle. 10 milliliters times 20 drops per milliliter is 200 drops total. Finally, we divide 200 total drops by 16 drops per day. That equals 12.5. Think about how we round this day's supply. Correct. Option A is correct, 12 days. We round down to the nearest practical day. The trap here is OU. If you miss that it's for both eyes, you will calculate double the supply. Let's try a more complex drip calculation. A patient requires a dopamine drip at 5 micrograms per kilogram per minute. The patient weighs 176 pounds. The dopamine concentration is 400 milligrams in 250 milliliters D5W. What is the flow rate in milliliters per hour? Options: A, 30, B, 24, C, 45, or D, 15. This is a multi-step one. Take your time and hit pause. Step 1 is converting weight. 176 pounds divided by 2.2 gives us 80 kilograms. Step 2 is calculating the minute dose. 5 micrograms times 80 kilograms is 400 micrograms per minute. Step 3 is converting to an hourly dose. 400 micrograms times 60 minutes is 24,000 micrograms per hour. Step 4 is unit conversion. 24,000 micrograms is equal to 24 milligrams. Step 5 is finding the concentration. 400 milligrams divided by 250 milliliters is 1.6 milligrams per milliliter. Finally, divide the 24 milligrams per hour by 1.6 milligrams per milliliter. Do that final division to get the flow rate. Great job. Option D is correct, 15 milliliters per hour. Keeping your units straight between micrograms and milligrams is the critical part here. Let's handle a ratio strength conversion. Express the ratio strength 1 to 2,000 as a percentage strength. Options are A, 0.5%, B, 0.02%, C, 0.05%, or D, 0.2%. Pause the video and do the conversion. Step 1 is understanding what ratio strength means. 1 to 2,000 means 1 gram in 2,000 milliliters. Step 2 is recalling that percentage strength is defined as grams per 100 milliliters. Step 3 is setting up the proportion. 1 over 2,000 equals x over 100. When we solve for x, we divide 100 by 2,000. That gives us a decimal. Check your work. Spot on. Option C is correct, 0.05%. A quick trick is to remember that 1 to 100 is 1%, so 1 to 2,000 must be a much smaller number. Now for a compounding question involving displacement. You are compounding a suspension. The recipe calls for 15 grams of active powder. The final volume must be 120 milliliters. The powder displacement factor is 0.8 milliliters per gram. How much diluent or water must be added? Options: A, 120 milliliters, B, 105 milliliters, C, 12 milliliters, or D, 108 milliliters. Hit pause and calculate the volume of the powder first. Step 1 is calculating the volume occupied by the powder. We take 15 grams times 0.8 milliliters per gram, which equals 12 milliliters. Step 2 is finding the water needed. We take the total required volume of 120 milliliters and subtract the 12 milliliters taken up by the powder. Do that subtraction to find your answer. Correct. Option D is the right answer, 108 milliliters. You cannot just add 120 milliliters of water, or the final volume would be too high. You have to account for the space the powder takes up. Let's look at a business math problem. A pharmacy buys a bottle of medication for $40. The dispensing fee is $4. The pharmacy sells the medication to a patient for $65. What is the net profit? Options: A, $21, B, $25, C, $29, or D, $69. Take a moment to calculate the bottom line. Step 1 is determining the total cost. That is the drug cost of $40, plus the dispensing or overhead cost of $4, which equals $44. Step 2 is calculating net profit. We take the selling price of $65 and subtract that total cost of $44. Subtract 44 from 65 to see where we land. You got it. Option A is correct, $21. Remember that gross profit is just selling price minus drug cost, but net profit must account for the overhead expenses too. Here is a specific gravity calculation. What is the weight, in grams, of 400 milliliters of a liquid with a specific gravity of 1.15? Options: A, 348 grams, B, 400 grams, C, 460 grams, or D, 515 grams. Press pause and use the specific gravity formula. Step 1 is remembering that specific gravity equals weight in grams divided by volume in milliliters. Step 2 is plugging in our numbers. 1.15 equals x grams divided by 400 milliliters. To solve for x, we multiply the volume times the specific gravity. Multiply 400 by 1.15. Spot on. Option C is correct, 460 grams. Since the specific gravity is greater than 1, the liquid is heavier than water, so the weight in grams must be higher than the volume in milliliters. Let's tackle an electrolyte calculation. ATPN order requires 60 milliequivalents of potassium chloride. The stock vial is potassium chloride 2 milliequivalents per milliliter. How many milliliters are needed? Options: A, 15, B, 30, C, 120, or D, 60. Hit pause. Don't let the units confuse you. Step 1 is identifying the concentration, which is 2 milliequivalents in every 1 milliliter. Step 2 is setting up the proportion. 2 milliequivalents over 1 milliliter equals 60 milliequivalents over X milliliters. Finally, we divide the desired 60 by the concentration of 2. Perform that division. Correct. Option B is correct, 30 milliliters. Even though milliequivalents sound complex, you treat them just like milligrams in the calculation formula. Let's tackle a tapering question. A patient presents a prescription for prednisone 10 milligram tablets with specific instructions. Take 40 milligrams daily for 2 days, 30 milligrams daily for 2 days, 20 milligrams daily for 2 days, and 10 milligrams daily for 2 days, then stop. How many tablets total should be dispensed? Your options are A, 25 tablets, B, 10 tablets, C, 20 tablets, or D, 40 tablets. Go ahead and pause the video to work through the schedule yourself. Let's break it down. Since the tablets are 10 milligrams each, we just need to convert the daily dose into a tablet count. 40 milligrams equals 4 tablets. 4 tablets times 2 days is 8 tablets. Next, 30 milligrams equals 3 tablets. 3 tablets times 2 days is 6 tablets. 20 milligrams equals 2 tablets, times 2 days is 4 tablets. Finally, 10 milligrams is 1 tablet, times 2 days is 2 tablets. Now we sum them up. 8 plus 6 plus 4 plus 2. That gives us a total of 20. Let's lock that in. Spot on. Option C is correct. Tapers require calculating the sum of every single stage. Writing out the daily tablet count step by step prevents simple addition errors. Moving on to a complex dosing calculation. A physician orders a drug dosed at 250 milligrams per square meter for a patient. The patient weighs 143 pounds and is 66 inches tall. Using the Mosteller formula, what is the approximate BSA and what is the final dose? Here are your options. A is BSA 1.7 and dose 425. B is BSA 1.8 and dose 450. C is BSA 2.0 and dose 500. D is BSA 1.5 and dose 375. Hit pause and grab your calculator for this one. First, we handle the conversions. 143 pounds divided by 2.2 gives us 65 kilograms. 66 inches times 2.54 gives us roughly 168 centimeters. Now, into the Mosteller formula. We multiply 168 centimeters by 65 kilograms, then divide by 3,600. That gives us 3.033. We take the square root of that number, which results in a BSA of roughly 1.74, or 1.7 square meters. Finally, we calculate the dose, 1.7 square meters times 250 milligrams. The calculation gives us 425 milligrams. Check your work. Great job. Option A is correct. This is the ultimate layered problem because you must convert the height and weight first, plug them into the formula, square root the result, and only then calculate the final dose. Let's look at an insulin supply scenario. A diabetic patient uses Humalog Quick Pens, which are 100 units per milliliter. Each pen contains 3 milliliters. The patient injects 15 units 3 times a day before meals. How many boxes of pens, with 5 pens per box, are needed to provide a 90-day supply? Is it A 2 boxes, B 4 boxes, C 1 box, or D 3 boxes? Take a moment to crunch the numbers on the total units needed. Step 1 is finding the daily usage. 15 units, 3 times a day equals 45 units per day. Step 2 is the total requirement. 45 units a day times 90 days equals 4,050 total units. Step 3 is seeing what is in a box. 1 pen is 3 milliliters times 100 units, which is 300 units. Since there are 5 pens in a box, 300 times 5 equals 1,500 units per box. Finally, we divide the total need of 4,050 by the 1,500 units in a box. The math gives us 2.7 boxes. Think about what that means for dispensing. You got it. Option D is correct. You cannot dispense 0.7 of a sealed box, so you must round up to the nearest whole package size, which is 3 boxes, to cover the full 90 days. Next up is a business math question. A pharmacy's financial records show a cost of goods sold of $2.5 million for the year. The average inventory value is $200,000. What is the inventory turnover rate? Options are A 8.0, B 12.5, C 10.5, or D 5.0. Pause here and apply the turnover formula. Recall that the turnover rate equals cost of goods sold divided by average inventory. So we take 2,500,000 and divide it by 200,000. To make this easier, you can cancel out the 5 zeros on both numbers. This leaves you with simply 25 divided by 2. That calculation results in 12.5. Let's lock it in. Spot on. Option B is correct. This metric tells us how many times the pharmacy sold through its entire inventory in a year. A higher number generally indicates better business efficiency. Let's figure out an infusion time. An IV bag of 1 liter normal saline is running at 125 milliliters per hour. The nurse starts the infusion at 0800. At what military time will the bag be empty? A 1600, B 1400, C 2000, or D 1800? Hit pause and calculate the duration. First, remember that 1 liter is equal to 1,000 milliliters. We calculate the duration by dividing the total volume of 1,000 milliliters by the rate of 125 milliliters per hour. This gives us exactly 8 hours. Now we just add 8 hours to the start time of 0800. 0800 plus 8 hours brings us to 1600. The clock stops at 1600. Check your math. Correct. Option A is the right answer. 1600 corresponds to 4 p.m. Military time is a standard skill you will need in the pharmacy. Here's a calculation where accuracy is critical for safety. You have a 10 milliliter vial of epinephrine 1 to 1000. A physician orders a stat dose of 0.5 milligrams SQ. How many milliliters should be drawn up? Options are A 0.05 milliliters, B 5.0 milliliters, C 0.5 milliliters, or D 1.0 milliliters. Take a moment to translate that ratio strength carefully. The ratio 1 to 1000 means 1 gram in 1000 milliliters. We know that 1 gram equals 1000 milligrams. So we have 1000 milligrams in 1000 milliliters. If we simplify that fraction, it equals 1 milligram per milliliter. Now we just calculate the volume. We need a dose of 0.5 milligrams. Divided by the concentration of 1 milligram per milliliter, the answer is 0.5 milliliters. We have a volume of 0.5 milliliters. Let's lock it in. Spot on. Option C is correct. Knowing that 1 to 1000 equals 1 milligram per milliliter is critical. This concentration is used for anaphylaxis, while the weaker 1 to 10,000 is used for cardiac arrest. Let's handle a day's supply calculation. A patient brings in a prescription for ibuprofen 800 milligrams, 1 tablet TID-PC. The patient requests a supply sufficient for 4 weeks. How many tablets should be dispensed? A90, B60, C120, or D84? Pause the video and calculate the total quantity. First, let's decode the SIG. TID means 3 times daily. The PC means after meals, but that does not change the math. So 1 tablet times 3 is 3 tablets per day. Next, the duration. The request is for 4 weeks. Since a week is 7 days, 4 times 7 equals 28 days. Finally, we multiply the daily count of 3 tablets by 28 days. 3 times 28 gives us 84 tablets. Let's verify that. You got it. Option D is correct. Usually, 1 month is calculated as 30 days, but when a prescription specifically says 4 weeks, that is strictly 28 days. This distinction often appears in exam questions. Now for a concentration problem involving creams. How many milligrams of hydrocortisone are in 60 grams of 2.5% hydrocortisone cream? Options are A 150 milligrams, B 1500 milligrams, C 25 milligrams, or D 2500 milligrams. Hit pause and watch your units closely on this one. Percent implies grams per 100 units. So 2.5% means there are 2.5 grams of drug in every 100 grams of cream. We set up a proportion. 2.5 grams over 100 grams equals X grams over 60 grams. Solving for X, we multiply 2.5 by 60 to get 150, then divide by 100 to get 1.5 grams. We have 1.5 grams, but the question asks for milligrams. Exactly. Option B is correct. We have to convert that 1.5 grams by multiplying by 1,000, which gives us 1,500 milligrams. The trap here was the final unit conversion. Let's calculate an IV pump rate with an additive. A physician orders 200 milligrams of a drug to be added to 100 milliliters of normal saline. The drug is available in a vial concentration of 40 milligrams per milliliter. The infusion is to run over 30 minutes. What rate in milliliters per hour will you program into the pump? A210, B200, C100, or D50? Take a moment. Don't forget to account for the volume of the drug itself. Step 1 is to find the volume of the drug we are adding. 200 milligrams divided by 40 milligrams per milliliter equals 5 milliliters. Step 2 is the total volume. We add that 5 milliliters to the 100 milliliter bag, giving us 105 total milliliters. Step 3 is the time. 30 minutes is 0.5 hours. Finally, to get the rate, we divide 105 milliliters by 0.5 hours. Dividing by a half doubles the number to 210. Let's lock it in. Spot on. Option A is correct. This is a layered IV problem. For small volumes, the volume of the drug added is significant and must be accounted for in the total volume infused. Let's solve a reconstitution question. A nurse needs to administer a dose of 150 milligrams of an oral suspension. The bottle label reads, reconstitute with 80 milliliters of water to make 100 milliliters of suspension containing 250 milligrams per 5 milliliters. How many milliliters should the nurse administer? A4, B5, C6, or D3? Hit pause and filter out the information you don't need. The instruction to add 80 milliliters of water is just a distractor. We only care about the final concentration, which is 250 milligrams in 5 milliliters. We can set up a proportion. 250 milligrams over 5 milliliters equals 150 milligrams over X. Or simplify the concentration to 50 milligrams per milliliter. Then, 150 milligrams divided by 50 milligrams per milliliter gives us our answer. That calculation results in 3 milliliters. Check the options. Great work. Option D is correct. Reconstitution questions often contain distractor data regarding the water added. Always look for the final concentration string to perform the dose calculation. Let's tackle a common scenario you might face in retail pharmacy involving an antibiotic dosage change. A pharmacy technician receives a prescription for amoxicillin 250 milligrams capsules. The SIG reads 1 cap by mouth 3 times daily for 10 days. The pharmacy only has amoxicillin 500 milligrams capsules in stock. The pharmacist gets approval to change the prescription to the 500 milligram strength. How should the new SIG read to maintain the same daily dosage and duration, and how many capsules are dispensed? A. 1 cap by mouth 3 times daily for 5 days, 15 capsules. B. 1/2 cap by mouth 3 times daily for 10 days, 15 capsules. C. 1/2 cap by mouth twice daily for 10 days, 10 capsules. Or D. 1 cap by mouth twice daily for 10 days, 20 capsules. Go ahead and hit pause to work out the new instructions and total count. Here is the breakdown. Step 1 is to look at the original total dose. 250 milligrams taken 3 times a day equals 750 milligrams per day. Step 2 is to check our new stock, which is 500 milligrams per capsule. This is exactly double the original strength. Step 3 is the correction. To keep the drug amount at 250 milligrams per dose using a 500 milligrams capsule, the patient needs to take half of the capsule. So the frequency stays the same at 3 times a day, but the amount per dose changes. Step 4 involves calculating the total count. We need half a capsule, 3 times a day, for 10 days. That is 0.5 times 3 times 10. Lock that in. The math gives us a total of 15 capsules. Spot on. Option B is correct. The SIG is 1/2 cap by mouth 3 times daily for 10 days, dispensing 15 capsules. Whenever the stock strength is double the prescription, you usually cut the tablet or capsule quantity in half. Next up, let's look at a day supply calculation for pain management. A patient is prescribed fentanyl patches, also known as Duragesic, at 25 micrograms per hour. The SIG is apply 1 patch every 72 hours. The patient needs a supply for 30 days. How many patches should be dispensed? A. 30 patches. B. 5 patches. C. 15 patches. Or D. 10 patches. Take a moment to crunch the numbers on this supply. To solve this, we first need to convert the hours into days. The standard duration for a fentanyl patch is 72 hours. Since there are 24 hours in a day, 72 divided by 24 tells us that 1 patch lasts exactly 3 days. Step 2 is simple division. We need to cover a total of 30 days. So we divide 30 days by 3 days per patch. Check your work. 30 divided by 3 gives us a nice round number. Correct. Option D is the right answer. You should dispense 10 patches. The key here is always converting hours to days to keep your units consistent. Now let's move to a dilution problem involving stock solutions. You are asked to prepare 500 milliliters of a 1 to 500 solution using a 1 to 50 stock solution. How many milliliters of the 1 to 50 stock solution are needed? A. 50 milliliters. B. 5 milliliters. C. 100 milliliters. Or D. 10 milliliters. Grab your scratch paper and solve for the stock volume. We will use the concentration times volume formula here. First, let's visualize the ratios as fractions to make it easier. Our stock, or C1, is 1 over 50. Our desired concentration, or C2, is 1 over 500. Our final volume, or V2, is 500 milliliters. Setting up the equation, we have 1 over 50 multiplied by our unknown volume, equaling 1 over 500 multiplied by 500. On the right side, 1 over 500 times 500 simplifies to just 1. So our equation is now V1 divided by 50 equals 1. If we multiply both sides by 50, we solve for V1. Lock it in. The math tells us we need 50 milliliters. That's it. Option A is correct. You are diluting the solution by a factor of 10, going from 1 to 50 down to 1 to 500. So you need 1/10 of the final volume in stock solution. This next question focuses on pediatric safety limits. A 5-year-old child weighing 44 pounds is prescribed a drug with a recommended dosage range of 10 to 12 milligrams per kilogram per day. The physician has prescribed 250 milligrams daily. Is this dose within the safe range? A. No, it is overdosed. B. Yes, it is within the safe range. C. No, it is underdosed. Or D. Yes, it is slightly high but acceptable. Pause here and calculate the safe range to see if the prescription fits. First, we must convert the child's weight into kilograms. 44 pounds divided by 2.2 gives us 20 kilograms. Step 2 is calculating the low end of the safety range. 20 kilograms times 10 milligrams equals 200 milligrams per day. Step 3 is calculating the high end. 20 kilograms times 12 milligrams equals 240 milligrams per day. Now, compare the doctor's order of 250 milligrams to our calculated range of 200 to 240 milligrams. Lock that thought in. The doctor ordered 250, which is higher than our maximum of 240. Option A is the correct choice. No, it is overdosed. Safety checks often require finding the absolute minimum and maximum daily limits and strictly adhering to them. Let's look at a retail math question regarding pricing. A hospital pharmacy has a markup rate of 20% and a flat dispensing fee of $5.50 per prescription. If a drug costs the pharmacy $45, what will the patient be charged? A. $54. B. $50.50. C. $64. Or D. $59.50. Hit the pause button and work out the final price. Step 1 is to calculate the markup amount. We take the cost of $45 and multiply it by 0.20. That gives us a markup of $9. Step 2 is to add that markup to the original cost. $45 plus $9 equals $54. This is the retail price before the fee. Finally, step 3 is to add the dispensing fee. We take the $54 and add the flat $5.50 fee. Check your total. The sum comes out to $59.50. Spot on. Option D is correct. The important takeaway here is the order of operations. Apply the percentage markup to the cost first, and always add the flat fee at the very end. Here is a compounding question involving hydrogen peroxide. A pharmacy technician needs to prepare 500 milliliters of a 3% hydrogen peroxide solution. The pharmacy only has a bottle of 30% hydrogen peroxide stock solution available. How many milliliters of the 30% stock solution and how many milliliters of distilled water are required to compound this order? A. 150 milliliters of stock and 350 milliliters of water. B. 50 milliliters of stock and 450 milliliters of water. C. 30 milliliters of stock and 470 milliliters of water. Or D. 50 milliliters of stock and 500 milliliters of water. Take a second to figure out the exact volumes for both liquids. We are going to use the C1V1 equals C2V2 formula. C1 is our stock strength of 30. V1 is our unknown. C2 is our desired strength of 3. V2 is our total volume of 500. So 30 times X equals 3 times 500. 3 times 500 is 1500. Now we divide 1500 by 30 to solve for X. This gives us 50 milliliters. This is the amount of stock solution. However, we aren't done. We need to find the water volume. We take the total volume of 500 and subtract the 50 milliliters of stock. Lock it in. That leaves us with 450 milliliters of water. Correct. Option B is the answer. You need 50 milliliters of the 30% stock and 450 milliliters of water. Remember, you never add the full total volume of water to the stock. You add enough water to reach the total volume. This question tests your clinical judgment regarding lab results. A patient is receiving vancomycin. The trough level comes back at 25 micrograms per milliliter. The reference range for the trough is 10 to 20 micrograms per milliliter. What is the most likely clinical intervention? A. Increase the dose. B. Switch to oral administration. C. hold the next dose, and decrease the frequency or dose. Or D, maintain current therapy. Think about what the lab results mean before playing the solution. This is a clinical math interpretation. Step 1 is to compare the result to the reference range. The range is 10 to 20. The patient's result is 25. Step 2 is understanding the implication. 25 is significantly higher than the maximum of 20. A high trough level means the drug is accumulating in the body, which puts the patient at risk for toxicity, specifically kidney or ear damage. Lock that thought in. High levels mean we need to stop adding more drug to the system. Option C is correct. You would hold the next dose and likely decrease the dose or frequency. As a technician, recognizing that a high trough equals a toxicity risk is a vital skill. Let's do a quick volume conversion. Convert 2.5 liters to fluid ounces. Use the standard conversion, where 1 fluid ounce equals 30 milliliters. A. 83.3 fluid ounces. B. 75 fluid ounces. C. 60 fluid ounces. Or D. 250 fluid ounces. Pause and do the conversion now. First, we need to get everything into milliliters. We know that 2.5 liters is equal to 2,500 milliliters because there are 1,000 milliliters in a liter. Step 2 is converting those milliliters to ounces. We take our 2,500 milliliters and divide by the conversion factor of 30 milliliters per ounce. Check the math. 2,500 divided by 30 is roughly 83.3. Correct. Option A is the right answer. Memorizing that 1 fluid ounce equals 30 milliliters is essential for these types of quick conversions. Here is a prescription with a changing dosing schedule. The prescription reads, take 2 tablets stat, then 1 tablet every 6 hours for 4 days, then 1 tablet every 12 hours for 2 days. How many tablets should be dispensed? A. 20 tablets. B. 24 tablets. C. 22 tablets. Or D. 18 tablets. Hit pause and count up the total tablets needed for the whole therapy. The best way to solve this is to break it down into phases. Phase 1 is the stat dose, which is 2 tablets immediately. Phase 2 is 1 tablet every 6 hours for 4 days. Every 6 hours means 4 times a day. So, 4 tablets a day times 4 days equals 16 tablets. Phase 3 is 1 tablet every 12 hours for 2 days. Every 12 hours means twice a day. So 2 tablets a day times 2 days equals 4 tablets. Finally, we sum them up. 2 plus 16 plus 4. Lock it in. The total count is 22. Option C is correct. 22 tablets. Breaking complex instructions into chronological phases prevents simple addition errors. Let's calculate the volume needed for a nebulizer dose. You have a stock solution of 20% acetylcysteine in 30 milliliters vials. The order is for 600 milligrams of acetylcysteine to be used for nebulization. How many milliliters do you draw up? A. 6 milliliters. B. 3 milliliters. C. 30 milliliters. Or D. 1.2 milliliters. Take a moment to solve for the milliliters. Step 1 is to understand what 20% strength means. It means 20 grams per 100 milliliters. Step 2 is to convert those grams to milligrams, so they match our order. 20 grams is equal to 20,000 milligrams. So our concentration is 20,000 milligrams per 100 milliliters. If we divide 20,000 by 100, we get a final concentration of 200 milligrams per milliliter. Step 3 is the final calculation. We need 600 milligrams, and each milliliter has 200 milligrams. We divide 600 by 200. Lock that in. The result is 3. Option B is correct. You need to draw up 3 milliliters. Percent strength conversions are high-yield questions, so always remember that X% equals X grams in 100 milliliters. Let's tackle a TPN calculation for question 41. We have a TPN order containing 500 milliliters of 50% dextrose, 500 milliliters of 8.5% amino acids, and 250 milliliters of 20% lipids. You need to calculate the total daily kilocalories provided by this bag. Your options are A. 1,600 kilocalories, B. 1,350 kilocalories, C. 1,520 kilocalories, or D. 2,050 kilocalories. Hit pause now and crunch the numbers. Here is the breakdown. We have to calculate the calories for each ingredient separately. First, dextrose. 500 milliliters times 0.50 gives us 250 grams. Dextrose provides 3.4 kilocalories per gram, so 250 times 3.4 equals 850 calories. Next, the amino acids. 500 milliliters times 0.085 is 42.5 grams. At 4 calories per gram, that is 170 calories. Finally, the lipids. A 20% emulsion provides 2 calories per milliliter. So, 250 milliliters times 2 is 500 calories. Add those three values up. 850 plus 170 plus 500 equals 1520 total calories. Spot on. Option C is correct. Remember that dextrose in TPN is hydrous, so it is 3.4 calories per gram, not 4 like food carbohydrates. Moving on to question 42. We need to express 0.005% as parts per million, or ppm. Is it A, 50 ppm, B, 5 ppm, C, 500 ppm, or D, 5,000 ppm? Take a moment to work that out. Percentage literally means parts per 100. We want parts per 1 million. To get from 100 to 1 million, you multiply by 10,000. That means we move the decimal point 4 places to the right. If you take 0.005 and move the decimal 4 spots to the right, you land on 50. Lock it in at 50 ppm. Option A is correct. The fast trick here? To go from percent to ppm, just move that decimal 4 spots to the right. Question 43 covers inventory management. A pharmacy technician is checking inventory for atorvastatin 20 milligrams. The shelf minimum is 3 bottles, and the PAR level is 12 bottles. There are currently 2 bottles on the shelf. How many bottles should be ordered? A, 3, B, 12, C, 9, or D, 10. Pause the video here and decide your order quantity. First, check if we need to order. We have 2 bottles, which is below the minimum of 3, so yes, we order. The rule is to order enough to reach the PAR level, which is the maximum target. So we take the PAR level of 12 and subtract the current stock of 2. That gives us a total of 10 bottles needed. Option D is correct. Always remember, the PAR level is your target ceiling. You don't just order back to the minimum. You refill the stock completely. Next is question 44. Using Clark's rule, calculate the dose for a 6-year-old child weighing 60 pounds if the average adult dose is 500 milligrams. Your options are A, 250 milligrams, B, 200 milligrams, C, 150 milligrams, or D, 300 milligrams. Grab your calculator and solve this one. Clark's rule relies on weight. The formula is the child's weight in pounds divided by 150, multiplied by the adult dose. So, we take 60 divided by 150, which gives us 0.4. Now, multiply 0.4 by the 500 milligram adult dose. That calculates out to exactly 200 milligrams. Option B is correct. Clark's rule is generally considered more accurate than rules based solely on age because it accounts for the patient's actual size. Question 45 is a compounding scenario. A patient has a prescription for magic mouthwash. The recipe requires mixing equal parts of lidocaine 2%, diphenhydramine 12.5 milligrams per 5 milliliters, and Maalox. If the patient is to receive a total of 180 milliliters of magic mouthwash, how many grams of lidocaine are in the final bottle? A, 0.4 grams, B, 3.6 grams, C, 1.2 grams, or D, 12 grams. Hit pause and break this down step by step. First, we handle the equal parts instruction. We have 3 ingredients and a total volume of 180 milliliters. 180 divided by 3 means we have 60 milliliters of each ingredient. Now we focus on the lidocaine. We have 60 milliliters of a 2% solution. 2% means 2 grams per 100 milliliters. If we set up the proportion, 2 times 60 divided by 100 gives us 1.2 grams. Option C is correct. The trick is to isolate the volume of the specific ingredient first before calculating the solute weight. Question 46 is about accuracy. You weighed a compounding ingredient and obtained 2.6 grams. The actual required weight was 2.5 grams. What is the percentage of error? A, 2.5%, B, 10%, C, 0.1%, or D, 4%. Take a second to calculate the percentage. First, find the error amount. 2.6 minus 2.5 is a difference of 0.1 grams. To find the percentage, you always divide the error amount by the desired or theoretical amount. So we divide 0.1 by 2.5, which gives us 0.04. Multiply that by 100 to get the percentage, and we have 4%. Option D is correct. Always remember to divide by the quantity you are supposed to weigh, not the quantity you actually weighed. Question 47 asks for a temperature conversion. Convert 212 degrees Fahrenheit to Celsius. A, 37 degrees, B, 100 degrees, C, 0 degrees, or D, 80 degrees. Do the math, or use your memory for this one. The formula is Fahrenheit minus 32 divided by 1.8. So, 212 minus 32 equals 180. Then, 180 divided by 1.8 equals 100. So the answer is 100 degrees Celsius. Option B is correct. You might have also recognized that 212 Fahrenheit is the boiling point of water, which corresponds directly to 100 Celsius. Question 48 involves flow rates. A physician orders an IV infusion of 500 milligrams ampicillin in 50 milliliters normal saline to be infused over 20 minutes. The IV tubing set is a microdrip set. What is the flow rate in drops per minute? A, 150, B, 100, C, 25, or D, 50. Hit pause and calculate the drip rate. The crucial piece of information here is the word microdrip. That automatically tells us the drop factor is 60 drops per milliliter. The formula is volume times drop factor divided by minutes. So 50 milliliters times 60 is 3,000. Divide that by the time, 20 minutes. 3,000 divided by 20 gives us 150 drops per minute. Option A is correct. Watch out for that term microdrip. It is the key to solving the problem without being given a specific number. Question 49 is another compounding question. How many 150 milligram clindamycin capsules are required to compound 60 milliliters of a 1% topical clindamycin solution? A, 2 capsules, B, 10 capsules, C, 4 capsules, or D, 8 capsules. Take a moment to figure out the total dose needed. First, determine the total weight of clindamycin needed. A 1% solution means 1 gram in 100 milliliters. So for 60 milliliters, we need 0.6 grams. We need to convert that to milligrams to match the capsules. 0.6 grams is 600 milligrams. Now divide the total milligrams needed by the strength of 1 capsule. 600 milligrams divided by 150 milligrams per capsule equals 4. Option C is correct. We need 4 capsules to create this solution. Finally, question 50. A patient takes warfarin 5 milligram tablets. The dose is 7.5 milligrams daily on Monday, Wednesday, and Friday, and 5 milligrams daily on all other days. How many 5 milligram tablets are required for a 30-day supply, assuming we start on a Monday? A, 43 tablets, B, 30 tablets, C, 60 tablets, or D, 36 tablets. Pause the video and map out the schedule. Let's look at 1 week. On Monday, Wednesday, and Friday, the patient takes 7.5 milligrams. Since the tabs are 5 milligrams, that is 1.5 tablets. 3 days times 1.5 is 4.5 tablets. On the other 4 days, they take 1 tablet. So 1 week requires 8.5 tablets. A 30-day supply is essentially 4 weeks plus 2 extra days. 4 weeks times 8.5 is 34 tablets. If we start on Monday, the 2 extra days are Monday and Tuesday. Monday uses 1.5 tablets. Tuesday uses 1. That is another 2.5 tablets. 34 plus 2.5 gives us a total of 36.5 tablets. Option D, 36 tablets, is the closest answer and the correct choice here. While in practice you might round up to ensure they don't run out, 36 is the mathematical target for this exam question. And exhale. If your brain feels a little like Jell-O right now, congratulations. That means you actually did the work. Seriously, you just survived 50 of the toughest pharmacy math problems I could throw at you. If you can handle this video, the actual PTCB exam is going to feel like a walk in the park. Do me a favor. Drop your score out of 50 in the comments below. I want to see who the real math wizards are. And if you missed the mid-roll, this is your last chance to hit subscribe before you go take a nap. You earned it. Go hydrate, and I'll see you in the next one. Also, check out our other videos. To do that, click that channel logo in the middle of the screen to subscribe. Click on the cards to choose your next watch. Thank you again for watching, and good luck.